Hi everybody, welcome to another video in Calculus 1, section 4.5, optimization problem. So in this section, we will find the maximum or minimum in application problem. So the first one is plain old, it's just straightforward. What two non-negative real numbers with sum of 20 have the largest possible product? So now we'll translate the work problem into math problem. So first, we have two non-negative real numbers. So let that be x and y, and non-negative meaning greater than or equal to 0. Now, sum of 20 meaning x plus y equal to 20 and have the largest possible product. The product is going to be x times y and largest possible. So what we do is here we maximize it. So maximize the product xy. Yes, yeah. So now we just find x and y pretty much. Of course, we have the graph here. Worry about that later. Now, so we translate the work problem into the variables. Now we put them together as math problem. So we write let x and y be two non-negative real numbers meaning x greater than equal to 0 and y greater than equal to 0. What we do here is we're going to maximize or find the largest possible product. So the problem is maximize the product of xy. Right. Of course, we haven't used all the information given our problem. In our problem, we have x plus y equal to 20, right? So if we solve for y in terms of x, have y equal to 20 minus x. Right. Now that is very important because in our calculus, we only deal with one variable. When we try to find a maximum minimum, it has to be in terms of one variable only. And we substitute into y. So our problem is x, y 20 minus x. And multiply it out 20x minus x squared. Right. So certainly we try to maximize that. One more thing, in order to have the maximum minimum, we should have the domain of the problem or the boundary, because the function is continuous on a closed interval, guaranteed to have a maximum and a minimum. So we should have a closed interval. If not closed, at least we have some interval. Right, now, we did have x greater than equal to 0, so we know that 0 is going to be the lower bound. Now, we still need to know what is the upper bound. We have y greater than equal to 0, right? Now we have y equal to 20 minus x. I'm going to use that because y greater than equal to 0, so we're going to have 20 minus x greater than equal to 0 as well, right? Because y is greater than equal to 0 and y is equal to 20 minus x. So what I do is I just going to add x on both sides here. So we have 20 greater than equal to x. So this is one condition and this is 2. Now put them all together, we have an optimization problem. So the problem becomes maximize the product 20x minus x squared for x greater than equal to 0, less than equal to 20. So for x less than equal to 20, greater than equal to 0. So we don't have a closed interval for x, and that is our problem. So now we translated a word problem into a math problem. Right. The rest to solve this problem is pretty simple. First, we find critical points in between this, and then we test the boundary, test the point in the middle, or any critical point inside, and the biggest one is the max, the smallest one is the mean. So that's very simple. Right. So to do this one, first we do to find critical points inside 0 and 20. It could be an open interval as well, but that's wrong. So I will take derivative, which is 20 minus 2x, and derivative equal to 0, derivative does not exist. Derivative equal to 0. So we solve for x, move the 2x over 20 minus equal to 2x. So x is equal to 10. And 10 is only between 0 and 20, so that's what's good. And then our derivative does not exist. So derivative equal to 0, derivative does not exist, very standard for critical point. And derivative does not exist. This is a polynomial, it is defined everywhere, so we have none. Because derivative is defined everywhere. So we have one point, and that point is between 0 and 20, so that's one's good. So we have one critical point between 0 and 20. Next, we just put everything in the table. If it is a closed interval and we have the point, so we just put everything in the table using original function. X, and now the product is 20x minus x squared. Remember, original function, because we're trying to find the maximum of the original function. Right, the points we will test will be 0 and 20, those are the boundaries, and the critical point in between we have x equal to 10. But we want to put all of those values into the function, and then we evaluate. So I just use the list here. Hit stat, enter. Let's clear all of this. Clear, enter. Clear, enter. Clear, enter. Right. We have 0, 10, and 20. Then I highlight the L2 and the 20. Instead of x, I will use L1, so second and 1. 20x minus second and 1 square. And that gives us 0, 100, and 0. So this one obviously is the absolute max. So our conclusion is they ask for what is the largest possible product. We say the largest possible product is 100 when the number is equal to 10. If x equal to 10, substitute in here 20 minus 10 is going to be 10 as well. So here I say at x equal to 20, x equal to 10, y equal to 20 minus x or minus 10 is going to be 10. So we have 10 and 10. Our conclusion is, so our largest product is 100, where the two numbers are 10 and 10 and 10. Right. So that standard, rather simple optimization problem. So what we do is, of course, translate a work problem into a math problem, optimization problem. So we're going to have the function of one variable, either maximum, maximize, or minimize, either finding the maximum or the minimum for that function. It would be nice if we know a closed interval, but at least we should know what the variable we're looking for, the range of the number or the domain of the problem. So in that case, we need, if we have that would be nice. Put all of that together, we translate the work problem into a math problem. Then we do the math. Now, how do we actually do find the absolute maximum, absolute minimum? Here's some review. But before that, here's our just some step. The work or the application problem will be complicated. Sometimes, cannot be just summarized into this. But the idea here, of course, we try to find a function to be optimized. Could be maximize or minimize. Of course, we need the variables, possible raw picture, so the variables, and then identify the constraint. Meaning a closed interval would be very good. If we don't have that, at least an interval. Then express the objective function in terms of one variable and find its interval. Yeah, so we need a function to be optimized and the interval. And then use calculus to find maximum or minimum. Right. Now the review for the calculus. How do we find maximum and minimum? So it depends. If the interval is closed or there is more than one critical point in the interval, then we use the table. So if we have a bunch of points, use the table. If we have a closed interval and a bunch of points, or just a closed interval, use the boundary. Use the table. Now, on the special case, and we will see this quite often, if there is one critical point on the interval, the key here, because it's one critical point, then we can have a lot of other options. Of course, if there's one critical point, we still can use the table if we want to. So we can still use the table of original function. And if we want to, we still can do that. Certainly the table will work regardless of whether we have one critical point, whether we have the closed interval or not. If it's not closed interval, we have to find the limit on the boundary. Now, if there's one critical point, we can use the theorem that says a local extremum is also absolute extremum, but that has to be one critical point. Now, if we know it is the local extremum is also absolute extremum, so all we need to do is we use the first derivative test, meaning the sign chart. And then the second derivative test, meaning that if it concave up, there have to be a minimum. If it concave down, there will be a maximum. Either way, so when there's one critical point, we have three options here. And depends. If the second derivative is simple enough to do, we do that. If it's not, use the sign chart for the first derivative. Of course, we can also just use the table. Right, let's take a look at other example. Now, a ranger has 400 feet of fence for constructing a rectangular ground. So it looks like this. One side of the ground will be formed by the barn, so you don't need the fence on that side. 3 exterior fences and 2 interior fences will be part of the ground. So pretty much we're going to have in this portion what dimension of the ground maximize the enclosed area. So we're trying to find the maximum area here. So of course this picture is nice already because we have the variable. So let this side be x. So there are 4 of them, and then y. So what we try to find is maximize the enclosed area. And the area for one big rectangle is length times width. So x times y, pretty much. So try to maximize that function. So simple enough, right? Now, similar to the previous problem, we need to write everything in terms of one variable because this function has 2 variables. We have to write that in terms of one variable. Now, we have 400 feet of fence, meaning that 1, 2, 3, 4x plus y equal to 400. So that is the constraint of our problem. So for x plus y equal to 400. Of course, we can solve for x in terms of y or y in terms of x. I prefer to just write y in terms of x. Right? And we substitute into y here. So the problem is maximize the area function of x times y, but y is 400 minus 4x. Multiply it out, 400x minus 4x squared. Right, so that's good. We have a function to maximize and minimize. Now, what is the interval? Now, since this is a geometric shape, the measurement here, none of them can be negative. So we have to have x and y have to be greater than or equal to 0 as well, because the measurement cannot be negative. Right? So then we substitute this into here. So I have 400 minus 4x greater than or equal to 0. I will just to keep the 4x be negative, or if you want to subtract 400 on both sides. So negative 4x greater than or equal to negative 400. Now, if we divide by negative 4 on both sides to get back by x by itself, notice that if we divide by a negative number, we have to reverse the inequality. So that gives us x less than or equal to 100. Now put them together, we have x less than or equal to 100 and then x greater than or equal to 0. So that is our closed interval. So we have x between 0 and 100. Right, so we have the function to maximize and the interval. So the problem becomes so we will maximize the area function for x between this interval. So that is our problem. I'm not going to solve this because we just need to set up this problem. Because so this is exactly like what we did earlier. Find critical points, put in the table for this function, try to find the maximum. So that, yeah, we should know how to do that. What the focus in this section is, of course, how to set up the problem. So we just try to go over a few more examples, if possible. Right, now let's look at another example. An 8-foot tall fence. So I have the fence. I'm not sure if you can see this, but this is a picture. The fence is 8 feet. And then the fence is 3 feet away from the wall. Assume that the wall is indefinitely high if we need to extend as high as we want to. And now what we're trying to do is we try to have a ladder start from the outside of the fence and touching the wall, and of course it has to clear the fence. And the question is, what is the length of the shortest ladder that clears the fence and reaches the house? By reaches the house, we mean it will touch the wall. Assume that the wall can be extended indefinitely high. And in this case, the function is a bit complicated, so we're going to use the calculator to find the maximum and minimum. Of course, I also want to show you how to find the maximum minimum using the calculator as well. Right. Now, an 8-foot tall fence. So now we do the cross section and then we look at the problem here. So we have the house, and because that's the wall, we have the 8 foot tall ladder, a fence, sorry, that's the fence. And so this is 8 feet. And assume that the fences and the wall are parallel and perpendicular to the ground. Of course, we're not talking about the wall leaning that way and the fence leaning the other way. That would be a lot more complicated. But now this is 3 feet away, the fence 3 feet away from the wall. Now we'll try to find the ladder. And we'll try to minimize the ladder here. Okay, so that sounds like an interesting problem. Now, this is a little more complicated. So we'll introduce this. This is the length L. So our problem is finding x, where we have to place the ladder, and then the length L as a function of x. So in this case, we will find where should we place the ladder and how long the ladder has to be. So that is our problem. But the intermediate step we need to identify is this B, which is distance from the ground to the wall where the ladder touch the wall. Right, now, of course, we're trying to maximize, find the minimum length of the ladder. So the problem is minimize L. Now, what is the function in terms of x? Now, one thing we know that, like I said, assume that the wall is perpendicular to the ground and the fence also perpendicular to the ground. So what we do here, we see one big triangle here. L is equal to b squared plus x plus 3 squared, right? And Pythagorean theorem. So the length L is equal to (3 plus x squared, square root of 3 plus x squared plus b squared. Pythagorean theorem. right? Next, now try to minimize the square root of this is the same thing as trying to minimize the square of it, right? Think about if we're talking about positive numbers. Let me just give you some random number. Now, which one is the biggest one? Of course, 6. Now, if we square them, 4, 9, 25, and 36. Of course, 36 is the biggest one. So if we're talking about all the positive numbers, to minimize this is the same thing as minimize the square. Of course, if we're trying to minimize this, 2 is the smallest one, and the square of 2 is also the smallest one. So in this case, minimize this, which is the same as minimize L square. Because if L is minimized, L square is also minimized. So we minimize L equal to L square equal to 3 plus X square plus B square. Now, that's nice and all, but where's B? We need to write B in terms of X because a function can only be in terms of X, right? Only one variable. So how do we do that? Now, one thing we haven't used is this. Somehow we have to relate this together. Now, with respect to this angle, we have opposite, adjacent, opposite, and adjacent. So I will write tangent of, say this angle theta is equal to, with the small triangle, opposite over adjacent, and the big triangle, opposite over adjacent. So we have that, right? And now can we solve for x? Solve for b in terms of x. So simply cross multiply. So bx equal to 8 times 3x. 3 plus x, sorry. Right, that's cross multiplying. And then divide by x. So b is equal to, let's multiply this out, 24 plus ax over x. Right, multiply now 24 plus ax divided by x. That gives us b, which we'll substitute into here. So we found the function to be minimized. So we're trying to minimize this. The reason in this problem we will use the calculator because the derivative of this is a bit complicated. So that's why we use the calculator. Right. Now, as far as the problem need to be complete where we have the domain of the problem. So what is the domain for x? One thing for sure, since we divide by x here, it's not going to be 0. Besides, if this is x equal to 0, that means we're going to put the ladder parallel to the wall and it cannot touch the wall. Of course, that cannot be the case, right? If this is the ladder, whatever the ladder is where we put, if x equal to 0, that will be parallel to the wall. It's not going to work. Now what we do is we can put the ladder like this or very slide like this. If we want to, we get a very long ladder and we touch the wall like this and extend it very far away. X can be very far away if we need to, right? So that certainly works. So in this case, we don't have the upper bound for x and we will have the lower bound for that either. So in this problem, because x cannot be negative, definitely x cannot be equal to 0. because we cannot divide by 0. And because if x equal to 0, the ladder is parallel to the wall, we have so it cannot touch the wall. That doesn't work. So x pretty much can be anything from 0 to infinity, because like I said, we can put the ladder to be very long ladder, and we just touch the wall there and touch the ground way over there. So x can be, it shouldn't be long as we want to. So in this case we will say x not less than or equal to, x is going to be less than infinity, because we can extend x as far as we want to, and it's going to be greater than 0 because it cannot be negative. If it's negative, that means it's inside the wall already. The problem is not going to work. And besides x, the measurement cannot be negative, cannot be 0. So this problem we just have a positive number. Yeah, we still need to write that. Right. Now we will put them together and write that as a math problem. Like I said, we're not going to do this by hand, so we just write the problem. And then we use the calculator to do that, because I still need to show you how to use the calculator to do that. So we'll maximize, I'm sorry, in this case minimize this function for x not equal to, yeah, and because we don't have a closed interval, we might not have the answer. If it is a closed interval, if the function is continuous, then we guarantee to have a solution. We guarantee to have a maximum and minimum. Since this is not a closed interval, so this might not be a solution. Right. As mentioned before, the math is a bit complicated. If we take the derivative equal to 0 of that, so we just use a calculator here. Right, so first I'll enter the function 3 plus x squared plus, now in here we have a fraction. The top is 24 plus ax. The bottom is x. And then we square that again, right? And then let's see the graph. We don't see it, right? Notice that in this case x is positive, so if we want to, we can set up x to be positive. So we can zoom out and see until we see the problem. But let's say reasonably x cannot be negative, so let's say we go from -1, let's say -10 to 100. Okay, reasonably, let's say x could be from, let's say from negative, could be from 0 to 100, let's say, because in real life we, make it reasonable, right? A ladder, if it's more than, if x is more than 100, the ladder is maybe way too long. So let's put some common sense into this. And so that is x. The length of the ladder, of course, we don't know, but it's going to be something positive. But notice that this is L square. So let's say if the ladder, let's say 100 foot ladder, okay. Let's say the ladder is 100 feet. We have to square that because the function is square. So let's say the maximum, let's say if we don't know, just put any random number, maybe 1,000 would work. Who knows? Let's see a graph. So hit Windows, change from -10 to 100. The reason I don't want to put it 0, because if I put 0, it will not show the axis, the y-axis. You see, yeah, kind of right in the edge, which I don't want to see it like that. So let's put -10, so we don't have to see right on the edge. And also, if you want to, the y, let's say we have one tick for 100 each. So we see this is the function, and so 100, 200, and something here, right? So the function y values is about 200 something. Take the square root of that, so we have the length of the ladder. Right, now x look like there's the minimum values is around here, the lowest point here. So if we want to, we can refine the windows. Let's say instead of -10 to 100, we just need to go to 20 now. And let's say 2 for each unit. Now the function will look a lot better, and the minimum values will be around here. So it'll be 2, 4, 6, so about 6. Right, we actually can find the exact values for that. So by the way, of course, draw the windows and try to find, hit the windows and try to put some values to it. Of course, we can change any values we want to, but in this case, after we graph a few things, we adjust the windows to that, so that look nice. Now we can find the minimum of this graph. In that case, hit second, calculate second, and that trace button, second trace, because we're trying to find the minimum. Right, when we're trying to find the minimum, we're going to go to the left, give us the boundary, right? Every time we find the maximum minimum, we need to indicate the boundary. That's what we did here. But in this case, the calculator, we can tell we're going for the left bound there. So I hit enter, and I will slightly go to the right here and hit enter. So the calculator will find the minimum in this interval. And hit enter. And they give us, this is the minimum. So x is equal to 5.768 and y is equal to 224 something. Right, let's do that again. Second trace, number 3 for minimum. Let's go to the left of that and go to the right of the point. Now it will find the minimum on the left and on the in that interval, and hit enter one more time. We have that. So using calculator, x is equal to 5.769, and then y, in this case it is L square, is equal to 224.765. Right. Now when we're done, I recommend that we hit zoom number 6 to go back to the standard window. Of course, usually if you don't see that, you can also hit zoom out. And you don't see that, right? If you don't see that, try to put very big windows. Then that certainly you will see the graph. Yeah. If you don't see the graph, try to make a very big windows. And then try to zoom it back in. But this problem, we reasonably choose the windows. Like I said, the ladder in real life is not going to be extremely long. It cannot be extended. I mean, mathematically, it could be indefinitely long, but in real life, reasonably choose that. And then so L is about 100 feet max, right? And then we have L square, because the function is L square, so 100 square, so that's 10,000. So, and then X also, in real life, we're not going to put the ladder that is extremely, I mean, almost parallel to the ground, right? In that case, how you going to step on the ladder if it is like that, right? So, of course, you use some common sense and some critical thinking into the problem too, not just look at the math problem and do it like the calculator, right? So, bottom line is, in this case, we have the ladder of the minimum height, by the way. The minimum length of the ladder, we're going to take the square root of that. If you want to, variables y1, so that is the values of the function. By the way, when we find the minimum, the x values of, no, this doesn't work. Let's just take the square root of that. 224.765. So that is about 14.99. So the ladder is about 15 feet. So the shortest, the ladder with the minimum length is 15 feet. And because we can, the ladder is 15 feet, and we place the ladder that is 5.769 feet away from the wall. Because when we know the length of the ladder, we're just trying to touch the house and clear the wall, and that's certainly we will have the distance x. Right, so that is our problem. I just want to set up the problem, and then of course that's the most important of the problem. One thing I want to emphasize again is that when we try to minimize L, the any number, if that has the square root, we can square both sides, because if a number is minimized, the square is also minimized. Right, now let's go to another problem. A manufacturer produces 1 liter cans of soup. Find the dimension of the cylindrical can that minimize the cost of material to make the can, meaning to minimize the surface area. Of course, when we try to make the can, we have the piece of metal, right? We roll it up. We have the side, and then one on the top, one on the bottom. Assume that it is, in the ideal world, we don't have to do the welding on the top and the bottom. I mean the rim. Assume that's just a piece of metal that perfectly placed on the top, one place at the bottom. Assume that there will be no thing to draw on the top and the bottom. Right. So that's what we have. So now let's try to draw it. So let's say this is a cylindrical can. And there will be the radius, and there's the height. Right. Now, what we have in this problem is, it is 1 liter. So the volume is fixed. It's 1 liter, or 1,000 centimeter cube. Right? So I will write V equal to, what is the volume of a cylinder? So in terms of the volume, it's going to be the base area times the height. The base area is pi r squared, and the height is h. And this is 1 liter. So that's what we have as the constraint. Right. What we're trying to minimize the surface area. the amount of metal that makes the can, right? So how do we find the surface area of that? Now if we roll this out, we're going to have to unroll the can. We have one sheet metal. When we roll it up, it will make a can on the surface, and then of course the top and bottom as well. So there will be a top and a bottom. It is a circle of the radius R, and there are two of them. And this is on the side. We have two of them, one for the top, one for the bottom. Right. How do we find this? By the way, when we roll this up, this, of course, is the circumference of the circle is also the length of a rectangle, right? The length of the rectangle, when rolled up, it becomes the circumference of the cylinder. So if this is R, the circumference is 2 pi R for this side. And of course this is still H, the height. So the area here is equal to 2 pi R times H, right? And then we have two of this circle, one for the top, one for the bottom. For the dimension of cylindrical can, we assume that this is perfectly cylinder. We're not talking about the elliptical cylinder, which is a lot more complicated. So we have one for the top, one for the bottom, and each one of them pi r square, the area. Right, so that's good, right? And this is a function, and we need to minimize the surface area, so this is to be minimized. Now, we need to incorporate that into the problem, because we have two variables into the problem. That's never good. It has to be written in one variable. So should we choose H or should we use R? Right? What I see in this problem, there's R and there's R show up in two different places. So ideally, I just want to show for H. In that case, I can write everything in terms of R. So it's easy. From here, divide by pi r square on both sides. And we substitute into this H. So A equal to 2 pi R 1 over pi r square plus 2 pi r square cancel the pi, cancel a square with an R. So A is equal to, there's a 2, pi and R cancel out, times 1 over R plus 2 pi R square. So that is the function to be minimized. Right? Now the constraint. Notice that in this case, the constraint, R is the radius. If we want to, we can make the can that is extremely flat. That whole 1 liter. Or we can make the can that is extremely tall, like this. That's still whole 1 liter. So in theory, it could be any values. So R could be from 0 to infinity, because there's no really constraint. we can make it extremely flat or extremely tall like this, still hold 1 feet. However, as our calculation we come up with, it's not going to be any shape like this. It should be something that look reasonably like a can. And actually this is not that the size of the can look reasonably, but the math confirmed that it actually minimized the material to make the can as well. So I put that together, because you have 2 over r. I just add 2 to the r to the negative 1 plus 2 pi r squared. Right. So our problem becomes we want to minimize this. And we don't really have any restriction on r. Theoretically, it could be anything. Right. Now this one we actually do the math. Let's find the critical point. I will take derivative. Take down the negative 1 to have negative 2, or to negative 2, and the derivative of this plus 2. Take down the 2, give us 4 pi r. Yeah, pi is a constant. Right, now in order to find this equal to 0, we have, or the another says we have r to negative 2. I have to put all together in one big fraction. So if we need to put them in one big fraction, so we multiply r squared top and bottom to have the common denominator. Now let's combine them. Negative 2 plus 4 pi r cubed over r squared. Right, so we have the derivative. Derivative. Then of course equal to 0, does not exist. We can spell it. So equal to 0. So the math here is not that complicated. If we have one big fraction equal to 0, meaning the top is equal to 0. And does not exist, meaning the bottom equal to 0. If we have one big fraction. Right, negative 2 plus 4 pi r cubed equal to 0. Right. Now, just solve for that, move the 2 over 4 pi r cubed equal to 2. Divide by 2 on both sides. So r cubed is equal to 2 over 4 pi. Cancel out the 2 and the 4. We have 1 over 2 pi. And then of course that r cubed, so to get back to r, we have r is equal to cube root of 1 over 2 pi. And then the derivative does not exist, the bottom equal to 0. So r is equal to 0. Because it's not going to work, right? The radius cannot be 0. So of course we don't have that. Besides, if you put in the original prompt, it's undefined. So r cannot be 0. So we only have one critical point here. Right, there's a lot of different ways to do this, to confirm actually to show that it is the minimum. Right, so that doesn't work because 0 is not belong in 0 to infinity. So in this case we only have one critical point. By the way, when we check the cube root on both sides, do not put plus or minus. So that's, we don't have that, so we just have that. So we have only one critical point. One critical point in the interval of 0 to infinity. Because of that, when we're trying to find the minimum, there will be a couple ways to do that. I mean 3. We'll use the table, but since the boundary are not close, I have to use limit. That's what I don't want to do. Right. Of course, we can use the first derivative test when we do the sign chart. If it is the local mean, it will also be absolute mean. Or we can use the second derivative test, which I really don't want to do either, because taking derivative of this, actually it's not that bad. Yeah, let's take the second derivative. By the way, just on practical purpose, let's just find this number. The cube root is under math. Cube root of 1 divided by 2 pi. Make sure 2 pi is in the parentheses, like that. So it's about 0.5419. And you said, what is that in terms of unit? Right? So what is really a unit for this one? Is that original we have 1 liter, so this is 1 liter. So yeah, what's that? We don't really know. Right? But after that, you will see the problem actually turned out to be very nice. But regardless, just go to here. We need to show that it actually the minimum point. Even though we find a critical point, it may not be the case. Just make sure that it actually a minimum. So in this case, yeah, confirm that it is the minimum. So like I said, one critical point we can use second derivative test, first derivative test, or the table. And we use the second derivative test because derivative is simple enough to do. If the second derivative test fail, go back to the first derivative, because the second derivative there is the inconclusive case. Right, so take the second derivative, which is derivative of this, take out the -2. So -2 times -2 is 4 or to -3, and then derivative of this plus 4 pi. Now I will evaluate at this point. Second derivative equal to, so I have that values, right? I just say 4 times that number. If you want to do that number, you can just highlight, copy and paste. But a better way to do that is just this second, the negative sign. The answer will be whatever the last answer we have. So we're going to do that till the -3 plus 4 pi. And what we have is that number. What we really need is that this is going to be positive. So meaning that it is concave up. Therefore, it is the local mean at r equal to this. Now, this is the local mean. Because it's one critical point, it is also absolute mean as well. Yeah, so we find that if we want to build the can with the minimized area, then we going to have r equal to that. Now, if you want to actually have a better unit, you start want to use 1000 instead of 1. So if we use 1000 here, 1000 there, because cc is centimeter cube, so whatever we come up with, the unit is centimeter, so that will be better if we put 1000 there. And so this will be 2000, that 2000. Cancel out will be 1000. So if we want to do the math, we take the cube root of actually 1000 divided by 2 pi. We actually have about 5.4 centimeter. So the can is the diameter of about 10 centimeter. So this is 10 centimeter. So the diameter of the can is about this much, which is reasonable. This much. Yeah. So a standard paper is 8.5 inches wide, which is about 22. So about half of this page. Yeah, about half of this, about 4.25 inches. That is the radius. In that case, multiply by 2. I'm sorry, the radius is about 5.4. So the diameter, so the can is going to be about this size. The diameter will be half of the page. Right. Nice thing is we don't even need to do that. We do have r equal to that, right? 0.5 something, right? Let's do that and put it back in here and find h. At r equal to 0.5419, h is equal to 1 over pi r squared. So we have 1 over pi times that number square. Right. So 1 divided by pi times, yeah, whatever that number. I thought I put the parentheses. Right. That number is this. It's where that. I have 1.08. So what is the significance of this? Now, the nice thing is, this is the height. That is the radius. What is the significance of them? Now let's just divide them. Let's see. If we take this number, divide that number, have exactly 2. So what do we have here? The height is twice the radius. So in general, if we want to minimize the surface area of a cylindrical, any cylindrical shape, of a constant volume. If we want a constant volume, in order to minimize the material or minimize the surface area, we're going to construct the can so that the height is twice the radius, or the height is the same as the diameter. So in this case, the can is about the diameter is half of the letter pages here, the letter size here, and the height will be the same as the diameter. So the conclusion here is the can with the constant volume will have the minimized surface area when the height is the same as the diameter. So conclusion. Height is equal to twice the radius, or the height is equal to the diameter. And because we can show that it is in terms of centimeter, we can have the unit, but in general, it doesn't matter if it is 1 liter or 1,000 liter or whatever it is. If it is constant volume, if we want to minimize the surface area, choose the can that with the height is the same as the diameter. Having said that, sometimes it's not always about minimize the material. If we're talking about a soda can, for example, if we choose the can that minimize the surface area, it will be very difficult to hold. The can will be this height and the diameter will be difficult to hold. So in that case, some other business reason that involved to it to make the can that is easy to hold in the hand, and that has nothing to do with minimize the material. But it is problem because we just try to minimize the material, right? Which is that. Right, I think that's interesting. Next, I just want to go over a few more samples, 2 more exactly. Suppose that an airline policy states that all baggage must be in the box shape, that box, with length, width, and height not exceeding 64. So we have the height, the width, and the length don't add up to, have to be less than or equal to 64. What are the dimensions and the volume of the square base box? To make things easier, we choose the box that have the square base. So the base of the box is a square, and then the height. Right. What we have here is length, width, and height. Length and width, which is the same, and height will be less than or equal to 64. And what are the dimensions of the square box with the greatest volume? Greatest volume. The volume is length times width times height. In this case, length and width the same times height. So W square times H. And we try to maximize this, so this function to be maximized. Right. And this is the constraint. We don't want the box to be any bigger than this. Now, think about this. If we want the box with the biggest volume, right, we're going to choose equal to. So that is pushing the boundary. We choose the biggest possible thing, 64, because if we have allowed to have 64 inches when total length, width, and height add up to 64, we're going to choose 64, right? We're not going to choose anything smaller than this. If we want the maximum volume, we have to choose the equal sign, choose the possible, biggest possible constraint. So in this case, we choose that to be equal to, even though we said not exceeding, but we pushing the boundary, we choose exactly that. So we're going to be 2W plus H equal to 64. If we want the maximum, choose the biggest possible constraint that we can have, which is right on the 64, right? Now, and then of course here we can solve for h. 64 minus 2w, and I can substitute into h. Right, so we have the problem is maximize the volume and h is equal to 64 minus 2w. I have 64 w squared minus 2w cubed. Yeah, one function of one variable, which is good. Now, the constraint, of course, just any measurement w cannot be negative. So w is greater than or equal to 0, greater than or equal to. Yeah, we can say just greater than 0, but yeah, we can just make them equal to 0. Because in this case, we can make it equal to 0. This function can be equal to 0. Right. So we have the constraint here. W is going to be greater than 0 or equal to. It doesn't matter. Because the height also need to be positive. Measurement cannot be negative, or it can be even 0. As I said, you can make it equal to 0 as well. It's no big deal. Right, now h is this. Substitute that into here, so we have 64 minus 2w has to be positive. So I solve for that. Move the 64 to the other side. Negative 2w greater than negative 64. And now divide by negative 2 on both sides. So w, remember, every time divide by negative number, reverse inequality. Yeah. So the width cannot be more than 32. This is very we know it's not going to, in reality it's even smaller than this, because if we have 4, if we want to max the width, never mind, but just less than 30, that's good enough, greater than 0. So the problem becomes maximize the volume 64w squared minus 2w cubed for w between 0 and 32. Right, now the problem is still the same thing. Would we build a box that is extremely shallow, or it is extremely tall, like a fish pond? Right. Now the airline is very small. They put 64 like this. So in reality, you cannot have anything that is longer than 64 inches. Right. So they don't put the constraint in terms of volume. They put the constraint in terms of 64. In that case, so the length, the width, and the height, none of that can be more than 64 inches. So even though if you carry the fish pole or the golf club or anything, it have to be less than 64 inches, or otherwise it will not fix this criteria. So they do not constrain in terms of volume, they constrain in terms of the length, which is smart. Because if they said anything is less than 1 cubic feet, in the last problem you can have extremely long object, and that will not be able to fit on a plane if you have that. Alright, so that is a problem. The math in this problem will be relatively simple. So critical point in that interval, so we don't, yeah, that's this one. Critical point in 0 to 32. Right, take derivative equal to 0. It should be simple, right? Derivative, take down the 2 times 64 is 128 w squared minus 6 w cubed, 6w squared. Right, equal to 0, does not exist. So 128 w squared, w not the square, 128 w minus 6 w squared equal to 0. Right, factor out the w, actually there may be 2w, and then we have 64 minus 3w equal to 0. So in this case, let that equal to 0, or 64 minus 3w equal to 0. So w equal to 0, or w equal to 64 over 3. And since this is between 0 and 32, there's only one. That is between 0 and 32. 0 doesn't count. Yeah, of course we can choose 0 too. If we put 0 in here, the volume is equal to 0, right? Because if one side is equal to 0, then volume is equal to 0. So that cannot be possibly the biggest volume, right? We want the greatest volume. 0, certainly not that. Right, does not exist, there will be none, because that function, that derivative, continuous and defined everywhere. Right, so we have only one point. That is very important, because if we only have one critical point, there's a lot of options to show that it is the absolute maximum or absolute minimum for that matter. So conclusion is there is one critical point in the interval. Because of that, you can use the second derivative test, first derivative test, or just use the table. But if the function is simple enough, I prefer to use the second derivative test, because I only need to test one point rather than use the sign chart for I have to test a bunch of points. So I take the second derivative, be 128 minus 12w now I'm going to put w equal to 64 over 3. So the second derivative equal to 128 minus 12 w 64 over 3. 64 over 3, 3 and 12 cancel. That's, so we have 128 just times 64 over 3. That's negative 128. So because this one is negative, meaning that it is concave down, and so we have that point is the local maximum. If it is the local max, because it is only one critical point, it is also absolute max. So we have that. Now the conclusion at the end. Answer at the end. We have W, the width is equal to 64 over 3. So let's calculate the height. Width equal to 64 over 3. And the height is equal to 64 here minus 2 times the width. So what's that? 64 minus 2 times 64 over 3. Math. 64 over 3 as well. So what do we have here? The width, this is square base, so the width times the width and the height turn out to be the same thing. So the answer is it's going to be a cube. 64 over 3, so it's about 21.3 inches. So if we want the box with the maximum volume, it's going to be a cube. 21 inches, 21.3 inches on each side to maximize the volume. So maximize volume. So the box with the maximized volume. So the box with the largest volume has the dimension 64 over 3 by 64 over 3 by 64 over 3, which is a cube of this size, inches. And the volume, of course, is 64 over 3 cube. And volume is equal to 64 over 3 cube. And the unit is inches cube. I have to redo this problem because the first time I didn't like the way I do it. Right, so the problem, we have a boat on the ocean that is 4 miles away from the nearest point on the straight shoreline. So we have a straight shoreline. And a boat 4 miles away from it. So this is where the boat's at. The shortest distance from the boat to the shoreline is 4 miles. Right. And that point is 6 miles from a restaurant on the shore. So let's say if we go this way 6 miles. And there's the restaurant here. That distance is 6 miles. Right. A woman plans to row the boat. So the boat's here. Try to row the boat to the shore and then walk along the shore line to the restaurant. So there's a lot of options. If she wants to, she can just row straight to the restaurant. In that case, she doesn't have to walk. Or she can row directly to this point and then walk for 6 miles. Or she can just do both. So row somewhere to a point on the shoreline. Of course, it should be in this direction. It would be not the right choice if you row the other way and then walk more than 6 miles. So it should not be the case. It have to be in the same case here. And then she will walk along the shoreline to that point. So there's 3 different ways. One to go 4 miles, row 4 miles and then walk 6 miles. And one is to just row directly to the restaurant, and or the combination of both. Just row at some angle and then walk the rest. Right, so that's what we have. So if she walks at 3 miles per hour and rows at 2 miles per hour, at which point on the shoreline she needs to land to minimize the travel distance. So in this case, let this distance be x, and we're trying to find that distance x. Right, now of course how to set up the equation. Now first, let's write out on the water she needs to row. So the distance is going to be, if this is the right triangle, the distance that she row is going to be 4 miles, and then x, that is the right triangle. So Pythagorean theorem, the distance is going to be equal to square root of 4 squared plus 6 squared, or 4 squared plus x squared, I'm sorry, where x is the distance from that point closest to the boat to the point that she needs to land. So that gives us square root of 16 plus x squared. So that distance, the speed, she row at 2 miles per hour. So in that case, what would be the time? Let's say the time that she spent rowing, T sub R. So what is the time that she spent rowing? Right, so now we have speed is equal to distance over time, right? So in this case, if we want time, it's going to be distance over speed. So the time that she spent rowing. Now of course, if we want to put in the proper unit, it's a distance over speed. The distance is square root of 16 plus x squared over speed 2. Now if we put all the unit into it, we have square of 16 plus x squared, the distance would be miles, over 2 miles per hour. So we have square root of 16 x squared over 2, and then mile on the top, mile per hour at the bottom. We're going to flip, and miles cancel out. So we have the unit here, of course that will be in hour. So that is the distance rowing, and the speed and the time. Now how about walking? The distance walking, this will be easy. The total distance is 6 minus x. So distance is 6 minus x. If we want the unit, that will of course will be miles. The speed, the walking speed, 3 miles per hour. And what is the time that she spent walking? So once again, the time is equal to distance divided by speed, and the unit for that, if we do once again miles over miles per hour, mile cancel out, we left with hour. So that is rowing, and this is walking. Now, what we need to do, of course, is minimize the time. So we try to minimize the travel time. So the problem is minimize the travel time, meaning minimize the time rowing plus the time walking. Let that be the total time t, capital T. Yeah. So minimize t. So of course t is equal to, we just add these two together. 16 plus x squared over 2 plus 6 minus x over 3. Of course, we will minimize this function and then limit on x. Alright, x, if x is negative, it will be over here. So she wrote in the wrong way in here, and then she had to walk a lot more than 6 miles. So that x should not be on this side, x should be on this side. So x cannot be negative, and also cannot be more than 6. That's not the right choice if she roll all the way here and then walk backward to the restaurant, right? So ideally, she roll in the same side and then walk. That will give us the optimal time. Of course, she can go here and then walk more than 6 miles, or she can roll all the way there and then go back. Either way, it's not going to give us the optimal time by common sense, right? If we want to get to that, it's not going to work if you roll all the way there and then walk backward. Why don't you just roll straight to that point? That would be a lot faster, right? Also, she's not going to go backward because going this way will be a lot faster. The ideal time, of course, is going to be somewhere in the middle. That's what we're trying to find. So the problem now is because minimize this, and then for x is between 0 and 6. So the point have to be within here. So our problem is minimize I will rewrite this as 1/2 16 plus x squared to the 1/2, that is square root. And then I'll split this. If we split this, we have plus 6 over 3 minus x over 3. Right, if I split that, that gives us 2 minus 1 over 3 times x. I will rewrite this as that. So plus 2 minus 1/3 x. Of course, for x between 0 and 6 could be equal to 0 and 6. Right, so that is our problem. The solution will be similar to what we have been doing. Find critical point. Critical point on 0 and 6. So first, of course, I will take derivative as 1/2. Take down the 1/2. Original power. I'm going to use the chain rule here. So it will be 1/2 parentheses to negative 1/2, and then the parentheses prime. Be 16 plus x squared. 16 plus x squared. Derivative of 2, derivative of constant is 0, derivative of this minus 1/3. So let's rewrite this. 1 over 4 so 1 over 4, and we still have 16 plus x squared to the negative 1/2, and derivative of 16 plus x squared is 2x minus 1/3. Right. Of course, I can cancel the 2 and the 4, make 2 at the bottom. So I have 1 on the top, 2 at the bottom. This negative power move to the bottom as well. And then of course the x there, right, minus 1/3. Now we try to get a common denominator and combine them. Right. To get to a common denominator, I will multiply 3 on the top and bottom. And the 1/3, I will multiply this top and bottom. I combine like terms. Three x, and then the bottom 6, 16 plus x squared, and the top we have that. Right. Since we have the common denominator, we can just combine them. Now we have the derivative, so equal to 0 does not exist. Very standard. When we have a fraction, that means the top is 0. And then the bottom equal to 0 when the derivative does not exist. So top equal to 0, 3x equal to 2, 16 plus x squared to the 1/2 equal to 0. I move this to the other side. Now we can square both sides. When we square both sides, we should check the answer. In this case, that should be simple enough. We just need to know that the answer, just need to show that the answer is between 2 and 6. That's all we need to watch out for. Of course, and at the end, we still put in the function to evaluate. So now 3x squared will be 9x squared. The square go to the 2 here, square go to 2, that 2 square is 4, and then the square go to the 1/2, 2 and 1/2 cancel out. That's 16 plus x squared. Now multiply it out, we have 9x squared equal to 64 plus 4x squared. Move the x squared, 4x squared over, we have 5x squared equal to 64. So x squared is equal to 64 over 5. And do so for x. Don't forget we take the square root on both sides. There will be plus or minus. So plus or minus square root of 64 over 5. Right. Keep that for now. Now let's go to the other side. Now the bottom equal to 0. This will be easy. Divide by 6 on both sides. Now I square both sides. The square will cancel with the 1/2 power. Give us just the power of 1. So we have 16 plus x squared equal to 0. Move the 16 over x squared equal to negative 16. So x equal to plus or minus square root of negative 16. And since negative inside the square root, that is imaginary. So in this case, we have not gonna have anything here. So the solution that is between 0 and 6. Now we test all of those points. This is not real, so it doesn't count. We're not going to count this. Between 0 and 6, there's only one of them. Square of 64 over 5. So on the interval of 0 and 6, or we can just say it on the open interval of 0 and 6, there's only one of them. Square root of 64 over 5. Or we can write square root of 64 over square root of 5, or 8 over square root of 5. 8 divided by square root of 5. So it's about 3.578. Right. So on that interval, there's only one point, one critical point. Right. Next, we go to a table to determine the values. So run out of space, so I have to continue on this note. On the table, of course, we use the original function. Right, so the time, the x, and the time of the function, original function, I'm going to use this one, 1/2 16 plus x squared to the 1/2 plus 2 minus 1 over 3x. So that is the time that's spent rowing and walking. Right. Of course, we have 0, and then 6 are the end point, and in between them we have 8 over square root of 5. Right, so I'm going to put that in the table and find the values. Right. Stat, edit, write the numbers 0, 8 divided by square root of 5, and then 6. L2, we have 1/2 will be 0.5 times 16 plus x squared to the 1/2. Also use 0.5 plus 2 minus 1 over 3 x. But of course we're not going to use x, we have to use the least one, right? So second one for L1. So we cannot put x there, we have to use L1 for x in the function. And we have these values 4, 3.6 and 3.49. Right, now let's go back to our problem. Our problem, minimize the time of the travel time. Now, if x equal to 0, meaning that C will roll straight to the saw line and then walk for 6 miles. If she does that, the total travel time will be 4 hours. Of course, 2 hours rowing and 2 hours walking, that's 4 hours. Now, if she wants to, she can just row directly from the boat to the restaurant, go straight. In that case, x equal to 6. In that case, the time travel is 3.6 hours. Now, ideally, she will go to the pond here and then walk the rest. And that's distance that she have to aim for where she try to land is 8 over square root of 5, meaning that's 3.578 miles away from the pond, directly from the saw line, directly the closest point to the boat. She has to go to aim for about 3.578 miles and then walk the rest. In that case, she will save about 0.1 of an hour, so it saves about 6 minutes compared to rowing straight. So the shortest distance from the boat to the restaurant, of course, it's going to be this. But the shortest distance does not result in the shortest time. The shortest time is rowing for a little and walk for a little. And in this case, this show that it has to be that much. And so she will walk about 2 miles something. Right, so of course, after the table, we conclude that the total minimum travel time is 3.49 hours. If she go to a point that is about 3.578 miles from the closest point to the boat on the saw line. Right, so you get the idea. Right, so of course this is absolute minimum. Right, so I thought this is an interesting problem. Now, in real life there are quite a few things that we can do using kind of similar things here. Now, imagine that we're not talking about the boat and then rowing and walking. I suppose kind of similar problem. Here. Let's say you have still I try to make it as similar to our problem as possible. Let's say we have an oil rig here. That is also 4 miles away from shore. The shoreline is, assume that is perfectly straight. Right. Now, suppose also that 6 miles down the road there is the oil refinery. There. Now, if that is the case, how do we build the pipeline? Of course, we can build the pipeline straight from here to there. Or we can build the pipeline straight to the saw line and then the rest. Now, the problem with this is the underwater pipeline is more expensive than the over the land pipeline. So in that case, it might be best if we just go at an angle. So we have some that is underwater pipeline and then some over the land pipeline. In this case we still have X. So kind of similar problem. Right? So in this case, of course, we have the over the land pipeline and under the water pipeline. This is over the water, over the land, over land, and then underwater. Right, underwater. Let's suppose that the cost is $3 million for a mile, and over land should be cheaper, only $2 million for a mile on land. Right. Now we know the distance is 4 miles and 6 miles respectively. Here, I mean the distance is not distance is going to be that and that. So how do we set up? Of course, we try to minimize the cost here. So how do we set up the equation? All right. First of all, what is the cost of the underwater pipeline? Of course, that's going to be the distance. So that is the distance in mile. So do we divide by 3 miles, $3 million a mile, or we multiply by it? So let's consider the unit. If we have 4 square plus x square mile, if we divide $3 million a mile, $1 million a mile. So if we're talking about the unit, we have miles on the top, and at the bottom we have $1 million a mile. Multiply reciprocal, we're going to flip this, and then we have mile multiplied by mile over dollars. Because that doesn't work, right? So we're not going to divide them. That doesn't make sense. Now, so if it is $3 million a mile, so how about if we multiply them, right? If we multiply them, the miles on top cancel with the mile at the bottom, and we end up being millions of dollars. So that should be fine. So that is perfectly fine. So the underwater is going to be 4 square plus x square times 3, and the unit, of course, million of dollars. So that is the cost of underwater pipeline. We do the same thing. It's going to be 6 minus x for over the land pipeline times 2, and the unit, of course, dollars, million of dollars. All right, add them and try to find the minimum. So this will be very similar type of problem, except make sure that in this case we have the times, the distance, and the speed. Just trying to show for the correct quantity here. Here we have the cost per mile, the $1 million a mile. We have the distance, and then we have the total cost of the whole project. In this case is multiply, the other case is divide. Yeah, just make sure that whatever we do, the unit has to work. So in this case, if we want the total cost of the project, it should be in $1 million. And to make sure that we have to match the unit. Right. Anyway, so I didn't want to do one problem like this, but at least just write out the comparison between our problem and plus this problem. Right. So anyway, I'm going to stop the section here. As always, thank you for watching. See you in another video in Calculus 1.